Hi, I'm Patrick Heath, Motor Control Manager for Microchip's 16-bit microcontroller business unit. Today I will be demonstrating our new dsPIC digital signal controller-based ceiling fan reference design for low-voltage BLDC or PMSM motors. This design delivers very high efficiency and is optimized for the lowest bill of materials cost. Best of all, this round board is just 10 centimeters in diameter, so it fits perfectly into the top of a ceiling fan motor. Ceiling fans are common in homes, offices, and buildings, especially in warmer climates. They work in conjunction with central air conditioning to circulate air and help keep us cool. A typical ceiling fan is designed with an inefficient single-phase AC induction motor, or ACIM. This type of motor is usually chosen because it is the lowest cost option, making the fan less expensive to produce. However, a standard ACIM burns about 100 watts per hour. When energy was cheap, this wasn't much of a concern. However, the cost of energy has increased significantly over the past several years. The ongoing cost of running an ACIM-based fan makes it difficult to justify its lower initial purchase price. A more cost-effective solution is to add electronic controls and use a high-efficiency algorithm called field-oriented control, or FOC for short, to power an efficient BLDC or PMSM motor. This solution can drop the power consumption down to 17 watts per hour, which could quite possibly recoup the increase in the fan's motor price in less than a year. Here is our low-voltage 45-watt ceiling fan reference design board, mounted in a 3-bladed ceiling fan that is powered by a 32-volt, 3-phase BLDC motor made by Nidec. This design combines the permanent magnet rotor in the BLDC motor and the implementation of FOC to provide a very energy-efficient solution. When the motor is spinning at 100 RPM, you can see that our dsPIC DSC-based reference design only draws 2 to 3 watts of power. If we increase the RPM to 200, it draws around 7 watts. Finally, if we increase the fan speed to 300 RPM, which is very fast, it only draws about 17.5 watts. This is the same amount of power as used by 2 60-watt equivalent LED bulbs, making it extremely efficient. The firmware used in our demo includes several advanced features. The first of these is called Initial Position Detection, or IPD for short. This software determines the exact rotor position at startup to ensure that the fan is always turned in the correct direction. Otherwise, half of the time the fan would move in the reverse direction for a brief time and then be quickly jerked in the other direction. Here you can see that the fan starts up smoothly in the correct direction each time that it is turned on. The demo software also includes Flying Start software. This ensures a smooth restart of the fan in case the power is cycled off and the fan blades are still rotating when the power is switched back on. The software detects that the fan is still moving and restarts it smoothly without creating any jolts in the operation. Here you can see another advanced software feature called braking. When the fan direction is reversed, it can be safely stopped from spinning in the current direction by electronically braking the motor and slowing it down to a stop. It is then started up normally to spin in the opposite direction. The efficient fan operation, speed control, and advanced features like IPD, flying start, and braking are all made possible by adding an electric commutation circuit to control the 3-phase BLDC motor. This all starts with a switcher from Power Integrations that creates the 32-volt DC power rail that powers the fan motor from the 110 or 220-volt input voltage. From the 32-volt power rail, we use a Microchip DC to DC converter and an LDO voltage regulator to further drop the voltage, as seen here in the block diagram. To implement the inverter circuit, we first need to rectify the 110 or 220 alternating current, or AC, voltage input to direct current, or DC. We used a low-cost Power Integrations LYT6068C-TL flyback CVCC switcher LED driver IC with an integrated high-voltage switch and flux-link feedback. It is very efficient, typically keeping the power factor correction, or PFC, above 0.9 when running at 225 RPM or higher. On the front side of the reference design board, you can see the transformer required to create the flyback circuit. This one comes from Worth Electronics. The MCP16331 buck regulator drops the 32 volts to 10 volts, which is needed to power the 3 MIC4605 half-bridge MOSFET gate drivers. It operates from input voltage sources up to 50 volts. Integrated features include a high-side switch, fixed frequency peak current mode control, internal compensation, peak current limit, and over-temperature protection. Minimal external components are needed to develop a complete step-down DC to DC converter power supply. The gate drivers pass through the PWM signals from the dsPIC DSC that turn the MOSFETs on and off to power the motor. Their 85-volt operational capability supports running motors up to 48 volts. 3 ROHM 100-volt 3-amp dual N-channel MOSFETs with a low 170 milliohm RDS on complete the inverter drive output to the motor. The 10-volt output level from the buck converter was selected to reduce the RDS on from the MOSFETs, which helps to maximize the overall system efficiency. A highly efficient MIC 5205 LDO voltage regulator drops the 10-volt power rail to 3.3 volts to power the dsPIC DSC motor controller. The MIC 5205 has an ultra-low noise output and a very low dropout voltage, offering better than 1% accuracy. Other key features include a reference bypass pin to improve its low noise performance, reversed battery protection, current limiting, and over-temperature shutdown. The heart of this reference design is a low-cost dsPIC 33CK DSC. Devices in the dsPIC 33CK family are available in a wide range of flash memory and package sizes. The dsPIC DSC's hybrid CPU combines the fast control loop capabilities of a digital signal processor, also known as a DSP, with the easy-to-use features of a microcontroller, or MCU. The on-chip peripherals are optimized for motor control applications with high-resolution PWM outputs, high-accuracy ADCs, fast on-chip analog comparators, and integrated op-amps with very low voltage offsets. This 28-pin DSC motor controller runs at 100 MHz with 64 KB of program flash memory. It runs the FOC algorithm, which derives the maximum torque and top efficiency from the 3-phase BLDC motor. To optimize the cost, only a single shunt resistor is used, along with an on-chip op-amp and comparator to measure the motor phase current and guard against an overcurrent condition. The dsPIC DSC provides the 6 PWM outputs to the 3 half-bridge MIC 4605 MOSFET gate drivers, which direct the MOSFETs to provide 32 volts to spin the BLDC motor. For communications and control, an IR sensor mounted at the edge of the board receives inputs from a remote control. This connector has several I/O pins that can support Bluetooth or other communication protocols. In our demo, we control the fan operation, speed, and direction using a low-cost IR remote control device, which transmits commands picked up by the IR sensor on the board. This fan reference design board can be used to spin any type of low-voltage 3-phase motor-based fan, such as a pedestal or desktop fan, or even the cooling fan in an air conditioner condenser. In addition to this fan reference design, we offer a series of motor control reference designs, including an air conditioner compressor and fan, a refrigerator compressor, and an e-scooter. The boards for these reference designs are shown here. We also provide an array of standard motor control development boards for different motor types and voltage ranges, application note code for a variety of motor control algorithms, and Motor Bench Development Suite, our premier FOC code generation GUI, all designed to speed up the development of your prototype application. To request a demo of the low-voltage ceiling fan, or to find out more about our motor control support, please contact your local Microchip sales office. You can also visit us on the web at microchip.com/motor to find out more about our motor control support, and at microchip.com/lvfan, where you can download the Altium design files, the source code, and the user's guide with schematics and a bill of materials for the low-voltage fan reference design board. Thanks for watching.